Hi, my name is Anirudh Joshi, and my final project is QANet. The task that this model is supposed to solve is the question answering task. This is a task that many NLP models benchmark against, and is a key task to really demonstrate natural language understanding. The task is essentially that given a paragraph or context, and a question about this, can the model answer that question correctly? This has applications from chatbots to even medical diagnosis systems, where based off some underlying corpus, the model can take in symptoms and give back diagnosis. The way we train and evaluate for this task is the SQUAD dataset developed here at Stanford. The dataset consists of these context paragraphs along with questions about that paragraph and ground truth answers. The model predicts start and end indices within this context that represents an answer, and those answers are verified against the ground truth. In SQUAD 2.0, which is what this project was on, there were also no answer questions, which are questions that don't necessarily have answers in the context, and the model is supposed to predict no answer. The motivation for this model is that in NLP, recurrent-based models were everywhere. But the issue is that these recurrent-based models are very slow because they're inherently sequential. You need to compute previous time steps to compute future time steps. While they weren't taking advantage of modern computing such as GPUs, which are inherently parallelizable. Convolutions and attentions are much more efficient in this regard because you can parallelize them efficiently. As mentioned before, one of the core innovations behind QANet, and including my custom implementation as well as the original paper, is this encoder block which does away with the recurrence. There are only convolutional layers, self-attention layers, and feed-forward layers. The self-attention that we use is the same as the multi-head attention that's used in the transformer paper, and allows for words and sequences to attend on other words with a constant path length. Further, there's something known as stochastic depth dropout, which is a way to regularize the model where blocks of layers are bypassed with a certain probability proportional to the depth of that layer. Another major component is the bidirectional context to query, and this was first introduced by BiDAF and allows the query to attend to the context and the context to attend to the query. The key differentiator here is that instead of producing a summarization, the attention weights are computed on every time step and propagated to future modeling layers. This allows for an improvement in performance as well as to less information loss. So this is the full architecture where initially you have the character and word embeddings, which are summed with positional encodings, which is the same as the sine and cosine ones used in Transformer. These are passed into encoder blocks for both context and query. Finally, they're passed into the attention layer, and then the stacked encoder blocks. And finally, probabilities are computed for the start and end token within the context that represent the answer. The results were surprising because they showed that BiDAF with character embeddings was actually the best model. Over here, the orange lines are BiDAF with character embeddings, the blue are without, and we see that the F1 and EM scores are significantly improve. These are the results from QANet with all the encoders, and while the EM and F1 scores initially decrease as expected, they don't increase as much and they stay pretty flat. We also see some significant overfitting after about 1 million steps. In order to figure out why this was occurring, I ran some ablation analysis to remove layers from this model and figure out which were the problematic layers. Here, the red lines show QANet without any encoder layers, and green are with. And as we see, it almost looks like removing the encoders layers actually made the model do a little bit better, but effectively they have very similar performances, which indicate that the encoder layers are the problem. I also visualized the attention heat maps to see specifically what the model was paying attention to during predictions. On the left, we have the query encoding attention map and the context encoding attention map in the first batch, so in the beginning of training. And on the right, we have them after 5 epochs of training. The first thing we see here is that none of the words attend to padding characters, which is a really good thing. And another interesting thing that we notice is the bottom right corner, the context attention map focuses mainly on the middle section. And this could be because most of the answers might be present in the middle of the context. So the model learns to focus on that in the context attention maps. So in conclusion, we saw that BiDef with character embeddings was actually the top performer, and this could potentially be because of issues with the QANet encoder, and not necessarily that QANet's architecture is not suited for this task. Future work can look into different objective functions. The objective function that we use, if you do really well on predicting the start index but don't predict the end index, your loss can still go down, but your F1 and EM scores aren't going to go up. Another change that could be made is also looking into the Transformer XL innovations to provide more long-range contextual understanding to these encoders to hopefully do well on longer contexts.